Хорошо. Okay. Today we continue the first meeting with Hilbert and Banach spaces, because the aim of our course, as we mentioned last time, is to consider properties of measures defined on the infinite dimensional spaces. Last time we began to discuss Hilbert spaces. I just recall that Hilbert space H is a linear space in which we have a node which is defined via scalar products for some elements, and it is a complete space. We said that Hilbert space can be characterized by two main features. One is dimension. Here I mean a linear dimension, and second one is separability. Last time we discussed what happens if the space will have a finite dimension. So we considered a case when linear dimension of H is less than infinity. In this case, we found we definitely have maximal linear independent system such that n is a dimension of H. And it was interesting to understand how we can write any element of H in terms of Fn. And we obtained a nice formula based on the Gram determinant. So let me just a few minutes continue discussing this formula. Let me recall you that when we have, for example, such system, we define Gram determinant of F1 Fn is a determinant of the matrix Fi Fj, which consists of the scalar product of our elements. This is very useful matrix, and let me show you why, at least one reason why it is useful. For example, relatively to those Kramer rule which we discussed at the end of the previous lecture, let us consider the following determinant: F1, 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 F2, and so on. But instead F1, Fk, I will put simply F1. So this is case place. Then I continue with the scalar products, ak plus 1, and so on, as usual, F1, Fn, F1, Fn, and the same happened in the every line. So here we will have F2 and so on, Fn, but everywhere outside of this rule we have scalar products like before at the Gram determinant, F1 and so on, and here Fn, Fn. Then if we consider such determinant, it can be easily defined. We just put vector instead of the number, in the appropriate place, then we get the vector. And let me denote this vector by hk. By hk. Then it can be easily seen that this vector is orthogonal to any vector fi hk is equal to 0, except I is equal to k. So for all other vectors, this vector is orthogonal, and fk hk is equal exactly to the ground determinant f1 fn. So one can conclude that hk is orthogonal vector to the linear span of f1 of all other vectors except fk. Now it's good to find the length of the orthogonal complement of fk to the linear span of other vectors. How one can do this? One can consider, let us find a square. Fk multiplied on hk square divided by the norm of hk square. This will be the square of the length of the orthogonal component of fk to linear span of other vectors. And we know already what is this. hk also can norm also can be very easily considered, very easily defined. It is equal to the sum. So norm hk square is equal to the sum. We just have to produce a multiple sum like this one. Ij equal 1 to n, fi fj, ijk, ik. This is, as usual, algebraic components in the round determinant for the indices jk, ik. And it's easy to check. It's easy to check that it is equal to the interesting expression like this one. It is equal to gram f1 fn and smallest gram where we exclude fk. I will denote this gram like jfk f1 fn. So this is also a ground determinant, but based on all vectors, excluding this vector fk. Please check this by yourself. Then one can easily obtain that this expression can be written as follows. It's equal to the ratio of ground determinant of all system divided by ground determinant of this system where we exclude fk. So this is a nice formula which I wanted to show you, which gives us a geometric meaning of the ground determinant, because if this is the square of the orthogonal component of fk to other vectors, then it is easy to understand that jf1 fn is the square of the volume Lebesgue volume, which for the parallelogram, which we obtain from vectors F1, F2. This is just a conclusion and some remarks about finite dimensional Hilbert space, and we will further denote it by Rn. So in finite dimension, we have this Rn with usual inner product, and that's all what we can say now about finite dimensional Hilbert space. Just some examples. This is one example, and another one will be useful for us if we consider L2. Here is omega P. This is the usual space of square degree functions of square degree random variables, which is defined on the probability space omega. But if omega is finite, and in this case f, of course, can be taken as a set of all subsets, and p I suppose to be just measure which gives positive weights to any component. I is greater than 0, and the sum, as usual, is equal to 1. This also a finite dimensional Hilbert space, which has a dimension equal exactly to the number of points in our probability space. Okay, now let's consider Hilbert spaces, which are linear spaces infinitely dimensional. As I said, a crucial role in the classification of these Hilbert spaces is played by the separability. So I will discuss a case when dimension of H is roughly right plus infinity, but H is separable. In this case, H has a count-of-dense set. Let us denote this count-of-dense set like Xn. Xn is dense in H. Then one can consider the following sequence of finite dimensional subspaces of H. We just denote Ln, define Ln as a linear span of first n elements from this dense set. X1, Xn. It is obviously finite dimensional space. We cannot guarantee that its dimension is equal to n, but this dimension is less or equal than. But what we know, if we denote by Pn, here is the intersection between analysis and probability, because usually in probability courses we said we take this capital letter P for probability, but in analysis people usually take this capital letter Phi for orthogonal projections. So I do the same in this Hilbert space. So Pn is orthogonal orthogonal projection. Orthogonal projection onto Ln. Onto what I can claim? I can claim the following: that Pn x tends to x when n tends to x, when n tends to infinity, for any x which belongs to our Hilbert space. Let us check this. So it's very simple to understand. Suppose this is our Ln. Here is our vector x, and here is its orthogonal. Complement to this space. So we just wanted to show that this one goes, this length goes to 0. But it is evident that if Ln is generated by the points x1, x2, and so on, here somewhere is xn, then of course this length, the difference between x and p and x, is less than minima of such distances. Yes, so one can conclude that the following relation holds: that norm of p and x minus x is less or equal to the minimum of the such set norm of x minus xk when k equal 1 to n. And due to the our hypothesis that xk form a dense subset in H, in H, then this goes to 0 when n goes to infinity. Okay, so one can conclude that Pnx is just approximation of every x. Then one can proceed as follows. If we define subsequently, the following vectors, here is E1 will be like x1. If it is non-zero, we always can suppose it is non-zero on x1, and then we just consider L1, L2, and so on. They are all related by such inclusion. And when we have the first Lk, which is not equal to L1, then it is evident, it is the first K. Then it is evident that we have here dimension equal to 2, and we can find vector E2 orthogonal to L1. So we just define the vector E2, which have this norm and is orthogonal to E1. And we will continue this procedure every time when we have new dimension. It will be rated only on the 1, so we can find the next vector, ek. In this way, we get a family or sequence of vectors E1, E2, En, and so on, such that they are orthonormal. The inner product Aj is equal to the Kronecker symbol delta Ij, and we understand that every Fn is just a linear span of some E1, Ek, depending on them. From this point of view, one can check that now any x have the following property. We can find for Pnx representation. It is equal to alpha 1 E1 plus alpha k n Ekn. What is interesting in this representation? When we take Pn plus 1 x, then the first coordinates remain to be the same, because they are, for example, this one describe the projection of our x onto the space L1. Next two describe the projection on the smallest space than Ln, and we have the following telescopic property. If Ln is included in Ln, then Pn from Pn is equal to Pn. Yes. So I call it telescopic because it is exactly related to the telescopic property of conditional expectation, which is actually a projection in the space of square decay random variable. So we have the same coordinates here, and this means that formally one can put into correspondence. One can put into correspondence for every x the series from n equal 1 to infinity. Here alpha n costs are equal to x en en, and due to the properties that Pnx approximate x, this sum converges in our space H. Finally, we have the equality norm of x squared is equal sum from n equal 1 to infinity, which is called Parseval identity. So in this case, one can see that all separate Hilbert spaces are more or less the same. We can say, yes, if we just fix this basis En, then one can say that H from X, here we take X, it is in one-to-one correspondence with this sequence X to N is greater than 1, and this sequence is an element of that small L2. I just recall you that this is the space of all real sequences which can be summed with a square, exactly like this, and correspondent norm is defined exactly like this. So we have one-to-one correspondence between X and such sequence. We have so-called isomorphism between L2 small and our H. But despite of this, that one can theoretically say, okay, all separate Hilbert space are the same, and does not matter in which space we are working. It is not true. For different applications in different space, let me just recall you that we have L2 omega Fp, and when omega is of complicated structure, then we discuss rather functions than their coordinates in some basis. Let me recall just the following very familiar to you example. For example, if here, instead of such general picture, I take 0 to pi with Lebesgue measure, with Borel sigma field and Lebesgue measure, then as the orthonormal basis, we usually take trigonometric system, sine, cosine, and so on. And we all know Fourier series. We all know a lot of sufficient conditions for Fourier series to be convergent in uniformly, for example, for good functions, or in some point for again for good functions, and so on. But let me ask you, can we easily check by the sequence of Fourier coefficients, do these functions have, for example, non-trivial interval as a set of zeros or not? If we just think a moment about such kind of question, we understand that sometimes it's better to say on the to speak on the language of functions, not of the coordinates in some basis. But formally, as I said, all separate Hilbert space are the same. They are at least isomorphic. So now let's consider example of non-separable Hilbert space. Non-separable Hilbert space. Let us construct it as follows. Take the real line R. And suppose that our H consists of all functions which are acting from R to R, such that the set of X, where f of X is not equal to 0, is at most countable. Is finite or countable. Also, I will suppose that we can define the norm of f square, which will be equal. I will write the sum as follows: fx squared. And you understand that this sum is properly defined, at least because we have such a condition on f, and we suppose that the sum is finite. Then one can imagine this elements of H like this one. Somewhere here we have some, here, somewhere here, and so on. So we have just countable number of points where f is not equal to 0. We have such condition, and one can define an inner product. In this case, properly, it is again sum with respect to R, fx jx. Okay, and it's easy to check that this is inner product. What remains to check, and this is exercise for you, just check that this is a complete space with respect to such node, and after we check this, we maybe easily can understand that this is non-separable space. Yeah. Why? Because if we take, for example, such a family of functions like f index x of y is equal just indicator of the set x from the point y. So this is just function which is equal 1 in this one point, and there are no other non-zero values. So this is such function, and then it's easy to check that they are all orthogonal. So that fx is orthogonal to f z when x is not equal to z, and that the norm of fx is equal to 1. So we have a non-counted set of vectors which are pairwise orthogonal and which have norm 1. So this space cannot be separable. Due to this example, one can understand that maybe the set of non-separable vector spaces are rich, and it will be hard to work in such space with the random elements. We will consider such examples in our course further. Now let me go to the Banach spaces. So now we will consider examples of Banach spaces, and here the definition is the following: that we have a linear space, and it is normed and complete. It is normed and complete. So we have B norm, and again we have to check different properties, different cases to get different description of the space. But it occurs now that even in a finite dimensional space, we can have a lot of norms. So let us briefly discuss a case when dimension of B is less than infinity. In this case, we know that B is that we have some linear maximal independent linear system here, and N is exactly the dimension of B. Then every x can be identified with the sum alpha 1 f1 plus and so on plus alpha n fn, and using such identification, one can say that maybe one can try to define some correspondence between B, here we have x, and these sequences alpha n, alpha 1, alpha n from Rn. We understand that this is one-to-one correspondence. This is one-to-one correspondence. Due to the properties of the norm, it is continuous and it is continuous in both sizes. It is linear correspondence, but now it is not, of course, an isomorphism, because if we take this vector alpha, then let us denote it for a moment alpha with arrow. Then norm of the correspondent element here is not a usual Euclid norm in alpha. But one can now say that, okay, our finite dimensional Banach space is maybe some Rn, but with the norm which is non-Euclid. Is non-Euclid. Non-Euclid norm. Then one can ask, what can be a characterization of this non-Euclid norm? How one can characterize non-Euclid norm? And the second question may be much more mathematically interesting: how one can characterize all non-Euclid norms in this space Rn? And it's actually easy to do if we take now such an interesting set in Rn. Consider the set of the such kind. I will denote it by S capital. This is the set of such alpha with arrow, such that norm this in which is induced by the our original Banach space. Then let us consider the set where it is equal to 1. What is this? This is like a unit sphere, but with respect to this norm. And what we can say about this is, one can check that this is a border. Of course, it is the border of the unit ball, and it is symmetric with respect to such operation when we take minus alpha. Yes, it is evident because norm of alpha is equal to norm of minus alpha. That's all. And it occurs that if we have such convex symmetric body which is compact in our space Rn, then it can be then its border can be its boundary can be a unit sphere for some norm. So norms in Rn, Banach norms in Rn are identified with such pictures. By the way, this also define a norm. Maybe you remember the norm of maximum of the absolute value. This is the norm related to the sum of absolute values of coordinates, and so on and so on. So any such convex symmetric body defined for us norm in finite dimensional Banach space. What is interesting? Of course, in arbitrary Banach space, the picture will be more or less the same. We will have a convex body which defines the norm, and let us see a difference between these two pictures. What is the difference? If we take here on the boundary some point, it belongs to the boundary with the interval. Yes, there are only few in this picture only 4 points which have no such property. But in this picture, every point has such property. So maybe we will see, and we will see in the future, that it is very important property of the which leads to the deep understanding of the geometry of related Banach space. That here the norm is roughly speaking smooth, and here is not. It leads to very interesting conclusions, but it is in the future. So we understand. Finite dimensional Banach space are related to such convex symmetric bodies in Rn, and this is Rn with some maybe ugly norm. That's all. Now let's go to the examples of the infinitely dimensional Banach spaces. Maybe the most important for at least for the random probability theory is a Banach space of continuous functions with the interval 0, 1. So now let us consider the space C 0, 1, C 0, 1 equipped with the norm of F equal to the maximum with respect to 0, 1 absolute value of Ft. It can be checked that this is the norm. It can be checked that this is a Banach space, so it is complete with respect to the norm due to the fact from calculus that the uniform limit of the continuous function is continuous function. It is not so. It is not so trivial now that C01 is separate, and there are different ways to prove this. One can be based on the approximation by polynomials. We know that polynomials are dense in this space. Then polynomials with rational coefficients definitely will be dense again in this space. But this is not the one way we can prove the separable. Don't use it polynomials without using polynomials. So we have a separable Banach space. Why it is so important for us? As I said, we will consider random elements here and probability measures on this space as continuous random processes and distributions of these processes in this space. This is one side. Another side is purely functional analysis reason. Then there exists an flow theorem, which says that if we have separable Banach space, just separable Banach space, of course real, every space is real in our course, then it is isomorphic to some subspace of C01. Yep. You see, this is a very interesting conclusion. Why? For example, from this inflow theorem, it follows that if you have Hilbert space L too small, it is isomorphic to some subspace of C01. And this is non-trivial. Why? Let me ask you firstly, why this is not the Hilbert space? Maybe we forgot something. Maybe some can define the inner product here in such a manner that this norm became to be Hilbert norm. No, it is not the case, and the reason is following. Let me recall you a well-known relation from school geometry that if we have if we have two vectors f1, f2, then one can define using this vector, and we have here the sum of these two vectors, f1 plus f2, and another diagonal will be f2 minus f1. And then it holds that now we have a very good relationship between the length of all these intervals which we have here, namely norm of f1 plus f2 square plus norm of f1 minus f2 square is equal to to what? Here we just have sum of squares of all this size, so 2f1 square plus 2f2 square. Okay. This is true only in the Hilbert space. It can be easily checked just when we apply here the scalar product, and here we just have f1 square, 2f1, f2 square, 2f2, and here we have plus f1, 2f1, f2 minus 2f1, f2, which is 0. So we have this equality, and please do two exercises. One is, please check that this norm does not satisfy this equality in general. And another one, just prove and flow theorem for dimension 2. So find two such continuous functions that with this norm they satisfy this equation. It will be very interesting to understand that we can do this, and it is not too easy to do. Okay, so we understand now that this is universal Banach space, and we will check its properties a lot of times further. Now, just let me announce another one spaces which you already also studied in the university. Let me recall you that there are some spaces LP for P is greater or equal than 1. LP is just a set of sequences xn, and is greater than 1 such that such a norm of x in power p, which is defined as a sum from n equal 1 to infinity, xn absolute value in power p is less than infinity. Okay. And we know from Minkowski inequality that this is Banach space, and one can check that it is separate Banach space. And here I just announce you a very interesting thing. You can think about it for the next lecture. Suppose that we have LP capital omega fp. LP capital omega fp. This is, as we usually denote, the space of all random variables which are defined on the general probability space with general probability measure and have again this moment, and the norm is defined as usual. The norm of psi is in P is equal to the expectation of absolute value of psi. This is the norm LP. This is the Banach space with the usual agreement that we have not random variable but class of equivalence of random variables. We don't distinguish between variables which are equal almost sure. So this is also a Banach space. You remember our last consideration related to Hilbert space was the following. This is isomorphic to any L2. Yeah. Here P is greater than 1. Of course, when P is equal to 2, we have this. What happened in other cases? Suppose we have P which is greater than or equal than 1. P is not equal to 2. It occurs that in this case, for general, of course, omega, for example, LP 0, 1, and it occurs that it is not equivalent. And we'll start our next lecture with the consideration of this problem. You can think about this problem by yourself. I just give you an advice. In this space LP, we have a sequence of independent Gaussian vectors. So this is the reason why we have no such isomorphism. Okay, for today we finished our lecture. We just trying to recall different Hilbert and Banach spaces, and next time we will continue with trying to understand what will be a suitable sigma field in such spaces, because as you remember, our main aim is to study the probability measures on such infinitely dimensional spaces. For today, this is all. If somebody have questions, please. Okay, if not, the lecture is over. Так,